Hi, my name's Jamie Riches and I'll be showing you the transmission electron microscope, or TEM, today. We'll use that to look at the gold nanoparticles in your experiment. So come with me and let's get the experiment underway. This is the TEM that we're going to use in our experiment today. So the TEM has the advantage over, say, the light microscope in that it's capable of looking at things at much higher resolution. A light microscope can only go down as far as 200 to 300 nanometres, whereas with the TEM we can see features that are as small as a nanometre or even less. But before we can do that, we're going to need to load our sample into the microscope. So we'll do that over here. Okay, so we'll load our sample into the microscope now. We've already applied it to the copper grid, and we'll put the copper grid into the tip, the removable tip you can see here. And so now we'll load that onto our sample rod, thus. And now we can put that into the microscope. Okay, so now we'll load the sample into the microscope. In order to do that, we have to put it into the airlock and then pump the airlock down so that the sample itself is at the same vacuum as inside the microscope. Okay, so we've loaded the sample into the microscope. Now what we need to do is to turn on the filament and get some electrons that we can use. So we turn on the filament here. So the filament itself, what we're doing is we're heating up the filament, and this is giving the electrons in the filament enough energy so that they can escape from the material. In our case, on this microscope, we're using a single crystal of lanthanum hexaboride, and the electrons, when they escape, we can go and accelerate them towards our sample and investigate it. Now, you'll notice that it's taking a little bit of time. We've got a progress bar here, which is slowly filling up, and the reason that it's taking this time is that the single crystal is fairly fragile, and if it heats up too quickly, the thermal shock can cause it to be damaged, and then we can't use our microscope. But in this case, the progress bar is just about filled up, so once that's complete, then we'll have a beam of electrons and we'll be able to go and investigate our sample a bit further. Okay, so we've got a beam of electrons we can play with now, and first of all we want to look at our sample at a low magnification. So if we put that up on the screen here, and if you have a look, you can see the electrons are hitting the phosphor screen at the bottom and they're producing a green glow, which means that we can see our sample. What we can see here on the screen at the moment are the black lines going across, and these are the copper bars in our grid, 3mm grid that we were looking at before. So the grid itself is about this size, and we can look for a suitable square here. This one here looks like it would be nice. And now we can go up and look at this at a higher magnification. And at this point, it's probably worthwhile going and having a look at things on the CCD camera so we can see them in a bit more detail. So we've got our sample in the microscope and we have a beam of electrons. We can now see the image on the CCD camera. If you have a look over here, we've already started a live recording. And you can see these black dots on a sort of pale background. So these are the gold nanoparticles that have been synthesized. And the size of these is going to be very small, it'll probably be on the order of 5 to 10 nanometers. We can investigate that by increasing the magnification. Because the magnetic lenses that we use have their strength changed just by increasing the current, it makes it very easy and accessible compared to, say, a light microscope. So now you can see the size of these particles is very easy to discern. We could stop there, and if we wanted to, we could measure out the size. A scale bar down the bottom is indicating that's an 80 nanometer scale bar. So again, these will be around about 5 to 10 nanometers in size. And you can see the shape of them. You could go ahead and make a size distribution and work out some of the statistics or the information about your sample. So currently we're sitting at about 80,000 times magnification. If we go up on the order of a few 100,000 times magnification, then we can start to see the lattice fringes that sit within our sample. And those are easiest observed over here on the Fourier transform, when we can see some of the spots that represent these fringes.
When a nanocrystal is oriented in a specific direction relative to the incoming electron beam, the atoms in the lattice planes are lined up, and the electron-specimen interaction leads to evenly spaced dark and bright strips, or lattice fringes, in the high-resolution TEM images.
Okay, so now we can see the lattice fringes that we have in our sample, and so this can give us the structural information. We can see features which are as low as about 2 angstroms in size, and we can use this to help identify what our sample actually is, in this case gold nanoparticles. We can also go ahead and we can change over from looking at the structural information to looking at the crystallographic information by having a look at the diffraction pattern, and this can give us some more information about the crystal structure of the sample. So I'll go ahead and do that now. Okay, so now that we can set up a diffraction pattern, and what we've done is we've gotten a group of particles that you can see over here on the camera. We've aligned them up so that there's a large number of these nanoparticles that we're going to take the diffraction pattern from. So I'll set that up now on the microscope and move into diffraction mode. Diffraction mode. Okay, and so now if we're going to go and take an image, we'll do that. And for the diffraction patterns, we often take a longer image because there's a large dynamic range that we need to capture. And over here on the screen, we should see that this image gets replaced by a diffraction pattern, which looks like this. So here you can see the central beam. These are for the electrons that have gone through and haven't been scattered by the sample. And then you've got a series of rings. The rings indicate to us that it's a polycrystalline sample, and the spacing of those rings indicates the spacing between the interatomic planes in the particles. And this is very characteristic of a certain crystal structure and a certain type of material. We can measure these and we can clearly identify that the sample that we're looking at is actually gold, as we expect. So it's a very powerful technique and one which a lot of people use in transmission electron microscopy. And now we'll go back to normal imaging mode. And at that point we probably have enough information from our sample to be able to carry out the experiment. So here I'd go ahead and then take out the sample and let the next person go and take out their experiments with it as well. Okay, so now we've taken some structural information on our sample and we've also gotten crystallographic information from the diffraction patterns. There's another type of detector that we can use on our microscope, which we haven't used today, and we don't really need it for today's experiment, but it's very useful for a lot of other experiments, and that's the energy dispersive X-ray spectrometer. So that's the instrument that you can see over here, which is attached to the microscope, and this one allows us to get the energy of the X-rays that are given off when the sample is illuminated with electrons. And this is important because these are like a fingerprint for the sample. We can tell what type of elements are present, and we can also condense our beam and scan it across the sample so we can work out the spatial distribution of the elements. We can see where the gold is in our sample and where the gallium is, if there's any there. In this case, we know that we've synthesised gold nanoparticles, so that's all we're going to see. So there's not really any value in using it today, but it's an important tool which you should keep in mind for future experiments. Okay, so I hope that you've learned something from today's video, and I hope that we might see you in here in the CARF labs in the future to use TEM in your research. And I wish you all the best with the rest of your course and your studies at QUT.